Oh my gosh. Is this happening? Is this real life?
No. All right, Thomas Almonds.
All right. No. How do I compute? That's probably me.
Oh, wow.
So mechanical.
You know, Thomas, how are you going to do that? Well, there's no letters on the keys.
Oh my gosh, I didn't even look and see. Now I'm going to be screwed up, man.
Now I'm jealous.
Yeah.
Mechanical keyboard. A good one.
I know.
The weird thing is, this one doesn't print out Stuart Penrose.
I know, I keep pressing it. Hi, everyone. Thank you for joining us. I'm going to give a fun little talk here. At least I hope it's fun. Hope you guys enjoy it.
Grateful Lambda.
Yeah, Grateful Lambda. Yeah. It's a functional bear right there. So this talk, oh, I have to let it be full screen. It's called Functional Programming Forever, and the reason is that I think you should use functional programming forever, for all time. I hope you guys enjoy it as much as I have. I feel like every talk should have a stiff-sounding subtitle, so I'll give this one a novel exploration of symbolic transformations across discrete domains. Really, really good stuff. So just to kind of get a census here, how many of you guys are programmers in your identify as programmers?
Does programmer count?
All right, so quite a few here. How many of you use what you would describe as functional programming languages regularly? And what sort of languages are those?
Delphi.
Delphi? Okay. Any others?
Scala.
Scala, F sharp, very nice.
Swift.
Swift.
Sort of.
So you guys are actually on a pretty far bent towards functional. So this talk is kind of just relaying my experiences, how I came to find functional programming, and some of the benefits that I've gotten from it. So who am I? My name's Thomas. I'm an engineer here at CJ. I blog at my website, and sometimes I tweet as well on the internet. So I really like functional programming, and this here was kind of my first introduction to it. Do you guys know what this image is from?
No.
SICP, that's right. Structure and Interpretation of Computer Programming. Kind of the junior engineer's Bible. There's this quote here that I love so much by Gerald Sussman. It's, every good wizard knows if you have the name of a spirit, you have power over it. So if you can give a name to a little piece of computation, you know pretty darn well what it's going to do. And it's funny, this whole idea of wizards too. It comes from there's this phrase grimoire, which comes from grammar, which is the same, like if the words of the thing is actually the magic itself. And I just always very, very nice to think of things like that. So I've got kind of a background. I started in JavaScript and Python, building apps in Django, jQuery, things like that. This guy over here, Hal, turned me on to a language called Clojure, which is a dialect of Lisp. From there, I kind of dived in head first. After that, I started getting into more typed languages like Java. If you see, Python, JavaScript, and Clojure, they're a little more dynamic. Don't have quite the sense of types. Java does, but it's lacks a lot of the functional things that I came to love from Clojure. So lately, I've been using a happy medium language called Scala. It's type-safe functional programming on the JVM, and I'll have some examples of that I'll walk through. So another is Another book that really changed my outlook is a book called The Little Lisper. And this book was written in the 60s, but it's still amazingly relevant today. And this cover is so cool because it's like it's kids' toys, and I think learning functional programming is a lot like going back and being that child who doesn't really who you have this sort of sense of wonderment at the way things work, but also there's an immediate frustration at things not working quite the way that they.
Hello. I'm outside your door, but I guess nobody can hear me knocking.
Which room, which door are you at?
Your office door, Conversant 250.
There's a.
I know where they are.
Okay, we'll come and get you.
So when you start to learn functional programming for the first time, you start to feel like a beginner again. But it's really nice that you feel like a beginner because you have to leave behind a lot of your preconceived notions about the way you did things before. So what does this book explain? I mean, the number one thing the Little Lisper is for understanding recursion. It's for understanding how to think in recursive terms. So it defines these things, symbols, it defines atoms, and then there's these things called lambdas, which really provide bindings between symbols and atoms. Atoms being just values. And the last thing that you really understand is recursion. So what is functional programming? You guys kind of have a functional bent. So could you guys throw out some definitions for me?
Stateless.
Stateless programming.
I would say describing what you want to get as a result rather than how you do it.
Okay, so what you want rather than how. Any others?
Referentially transparent functions as your modeling mechanism.
All right, so programs modeled through referentially transparent functions.
Yep.
Okay, these are all there are a lot of words here. I like this. I mean, maybe it's not a definition, but it's something that FP is. I'll just let you guys take a second and read it.
I'm having a bit of trouble to read it actually.
So it says, code written in Haskell is guaranteed to have no side effects. And the chief reason this guy says is because no one will ever run it. So I got this explanation from Wikipedia, this definition. It says, functional programming is a style of building the structure and elements of computer programs that treats computation as the evaluation of mathematical functions and avoids state and mutable data. It's all very clear to everyone, very sure. It's kind of so obvious. So why would you, what I might describe it as is simply just programming with functions. Some of the terms that people used here I would absolutely agree with, but there's a lot of context surrounding them. To understand stateless programming, you have to have a solid understanding of state. To understand referentially transparent functions, you need to understand what functions are, what it means to be referentially transparent. A lot of what functional programming is much like functional programming is built on top of these towers of abstractions. If you understand the little building blocks, the explanations are clear. But if you don't understand those building blocks, it's just jargon. So here's another little comic that I really love about functional programming. It's why is it so good? Why do we want to do it? Why are we here listening about it? And I mean, tail recursion is its own reward. It's like when you write that elegant functional programming, that program that so clearly describes what you want to do, rather than the steps to how to do it, then I think you have this sort of aha moment. So it's incredibly powerful, and I think a lot of that power comes from the expressiveness that you get from it. And honestly, I think it's a lot of fun. I think it's a lot more fun than writing, like the specifics of how you get something done, to just speak in these higher level terms. So that's that's functional programming. And my definition is, I would say you are doing functional programming when your primary unit of abstraction is a pure function. When you're trying to tease things apart in terms of pure functions, and I'll get to what it means to be a pure function a little bit later, but if that is how you abstract, then I think it is very likely that you are doing functional programming. I think a property of functional is that you get a sense of clarity through simplicity, not by modeling things, you know, as they would be in the real world, which sometimes can be incredibly complex, but rather by just having a single function that does one thing, and you can really just think in terms of the inputs of that function and think only about what the output of that function is.
Hello? Hello? Hello?
Hello, I just want to tell you I'm here for the CodeCraft meetup.
What door?
How would,
There's a letter on the thing.
what door? What?
There's a letter printed on the sheet, on the door.
Oh, it's A.
A, thank you, we'll come.
Back to your regular schedule.
So I think this idea of simplicity is incredibly, incredibly powerful, and I think it's actually overlooked a lot in the programming community. There's this really fantastic talk by this guy, Rich Hickey, called he's describing the differences between simplicity and something being easy, and that just because often these two ideas get conflated, people use them as synonyms. They say, oh, if something is simple, that means that it's easy. But it's actually not the case. Simplicity is about doing one thing, and easiness is about being so familiar that you can do it with your eyes closed. But that's not the same as, you know, like doing something incredibly complicated with your eyes closed. That's easy to you, but it is still not simple. So simple is about a single doing a single thing. So the other thing functional programming is about is fancy sounding words. One of the key pieces of functional programming is using words that other people don't understand. So there are a few that I've listed here. I don't recommend looking at them. I don't recommend looking them up. No, so again, it's not that these words are complicated by any means, but like I said earlier, they're built on abstractions. So you can understand these words in very, very simple terms so long as you have the lexicon, the sort of dialect to approach them. Does anyone here see any words they don't recognize?
I don't see any words. I
So you guys,
see Steve Buscemi.
so you guys know.
One and two.
I don't know a Varianic.
Okay. Does anyone here, on the other hand, know all of these words? And can give the definition for all of them?
I couldn't get the definition from Monad.
Oh,
understand
whoa,
kind of.
whoa.
Kind of.
You guys just
Func
cursed.
for, as soon as I learned Monad, Functor came up. I was like, Func.
So again, I'm not going. The point of this talk isn't to like be a dictionary where you can, you know, come out the other end and understand all of these, but hopefully you'll have a little bit more of an understanding of some of them.
Change the slide.
I don't want to look at Buscemi anymore. So again, I use this term pure functions. So what is a pure function? It's kind of a mathematical term, but it's just this diagram. If you understand this diagram, you understand pure functions. It's you got some input, and you apply some function to it, and that results in some output. So what we call that is we call it mapping an input to an output. So what that sounds pretty abstract, and it's like, well, you know, how is this different from like a procedure? How is it different from a subroutine? What is the difference between like just it calling something and having it be a, you know, I use the function keyword to define it, so that's a function. What makes it pure versus impure? Well, in pure functions, it's really, that's it, just input to output and nothing else. No talking to anyone else, no, like it is all you know about is that you got an input and you gave an output. You don't know about any implied environment. You don't know about any of the outside world besides your parameter list. And if you can still work only knowing that, then you are probably a pure function. So maybe we can approach it from the other point of view by looking at an impure function. So here's an example of an impure function written in a language called Python. So what we're doing here is we're building up a new array, and we take two parameters. We take an element, and for some reason we optionally take an array. You know, either we will create it for you, or you can give us one. Whether this is correct or not, you know, it's not for me to say. It's just an example. So what we do is we append an element to that array, and we return it. Is everyone clear on what this function does? So that array equals the two brackets there. That's Python has a feature called default values for variables. So it's that second parameter array is optional. If they don't provide it, we will use this default. So I use it here. I call new array 1, and it gives me back an array seeded with a value 1. And that's pretty cool. And it does what I expect. And so the other thing, I'm ready to start using this now that I've tested it a little bit. So I say, give me an array, and I want to start with 2 this time. And on that array, I want to append 3. So can anyone in here tell me what the value of my array is right now?
2 and 3.
2 and 3.
Oh, 1, 2, and 3.
1, 2, and 3.
Is it? 2 and 3 is 2.
2 and 3.
That's right, William. Whoa.
So the value of my array right now is 1, 2, and 3. And the reason is the default value becomes something like a static property of this new array function. It gets attached, and it's a mutable object. So if I return that object and I change it, what I'm actually doing is I'm changing the definition of this function. So when I call new array 1 again, I expect to get the same sort of result, because that's one of the properties of a pure function, is that given the same inputs, it must always return the same outputs. So here we see new array 1, it returns an array of 1, and down at the bottom I call new array 1, and I get this very, very different list. And the reason is because of mutable state. And it's because this program, this new array method, was defined in terms of mutable state. And then it exposed that mutable state incidentally, not on purpose, but it exposed that mutable state to the outside world. And so when someone starts working with the return value, they can actually change the definition of the function. So this is maybe an extreme case, and it's maybe, you know, you can get around it through a lot of ways.
Hello, what door are you at?
Door D, I think. South side.
Door D, we'll come.
Got it.
So how could we do the same sort of thing and have the properties of a pure function? One of those properties being, like I said, the same inputs always return the same outputs. So we can use a language like Clojure to do something like that. And what we do here is we just define the function twice. And this is actually what it means to be variadic. So variadic means that the number of arguments varies depending on how many are supplied. So I'm defined for one parameter. If you just give me an element, I'm going to provide you with this thing. And if you give me an array, I'll just use that array. So if you don't give it an array, it'll delegate to the two argument version. So I can call new array 1, and I get an array of 1. I can append 3 to a new array of 2, and I get 2 and 3. But the really, really important part is that calling it with the same arguments, I get that 1 again. So that's what it means to be a pure function. So the other thing to understand in this is that there are a lot of different programming paradigms out there. Maybe the oldest is imperative programming. And the style that when you're doing imperative programming, what you do is you structure your program as a series of sequential operations to evaluate. So you can imagine that as do this and then do that. As Boyan said earlier, it's very much how you do something. And functional, on the other hand, is defined in these units of abstraction, like I said, these functions, which are just abstractions. And when you speak in terms of these abstractions, you get to say what you want to do, rather than the sequence of how it's done. So the primary unit of the imperative programming language is the semicolon. It's the this statement is done, and now move on to the next. And the primary unit of functional programming is the function.
I thought it was the parentheses.
The parentheses. Yeah. There you go, call, right? That's yeah.
I would say it's the assignment operator.
The assignment operator in functional programming? Well, so
Okay, no, I'm just joking.
I'll cut you.
It's the monad.
And then finally, there's this whole paradigm over declarative programming, and that's really, I think, the other side of imperative. I think functional is really somewhere in the middle, because function application really still has this kind of order of apply this function and then apply this other function, but declarative really has the control flow completely abstracted. You just say what you want to happen and not how to do it, and you just trust that the engine that you're sending these operations to knows how to do it better than you. So some examples of this, like declarative programming languages, SQL is probably the one that most people are familiar with, but there are others. There's Prolog. There's a whole family, and this is really only like a sliver of the programming paradigms. If there's like more than I could list in an hour. So I really like this picture. It's a duck, I think. It's a rabbit, maybe, I don't know. It's
a book from Manning.
It's one of the. It's so.
Or O'Reilly.
So this is a class of optical illusions where you can look at it one way, and you get one perspective of the image. But if you look at it a different way, you see another. So these two protrusions, they could be either a duck bill or they could be rabbit ears, depending on how you see it.
Whoa.
And I think programming paradigms are a lot the same way. It's not that one is the solution. It's not that one really says what the real problem is and what the real solution is. It's just a way of looking at things. So programming paradigms are just patterns for programming. It's just a way we can approach these problems.
With one exception, functional programming allows for execution in parallel, where sequential programming is explicitly designed for a single processor.
Right. So one of the renowned benefits of functional programming is that parallel programming is easier. But I wouldn't say that it's fundamental. I think you can still use sequential programming and have it be parallel. It's just a bear. You have to use things like mutexes. You have to have a lot of artificial complexity just to deal with the programming paradigm. That's absolutely true. So each are built around these different constraints. Like they're, and I think it's important that they're constraints and they're not like features that they offer. It's not that, for example, when you're doing functional programming, you don't have to think about order, for example, because it's not imperative, so I don't need to think about this, then that. But rather, it's a different frame of reference to approach the problem from. Oh, no. It's my fault this time.
Wow, that's embarrassing.
What door are they at?
Yeah. So ultimately, programming paradigms are just ways to think about the problems that are in front of you, and they're tools that you can use to express different solutions. So I think a good way to start talking about what this thing really is to talk about collections. And what collections let you do is they let you treat many things as if they were one thing. So you can see there's like a lot of different fish here, but when you look at them together, they kind of look like one thing, and that's a lot like what a collection does. It takes many integers and lets you operate over them as if they were one. Has everyone worked with collections? Yeah? Right. Cool.
I got a huge collection at home.
So we're going to talk a little bit about how Java does this. Collections are in Java, and Java is, you can do functional programming in Java. You might go mad, but you can do it. So classically, in structured programming, the for loops were done through this series of these three terms. There's the initialization term, the termination, and the iteration. So we say when I initialize, I want to start at 0, and I want to continue so long as my number, my iterator is not as far as, or my counter isn't greater than the size of the list I'm operating over, and for everyone, we'll just increment the counter. So what we do here is we want to increment a list. Someone wants to give us a list of numbers, and we want to transform that list into a list where every number is one higher. So what we do is we take their list and we say, well, for every number, I'm going to get that number and I'm going to add 1 to it, and then I'll set it back into your list. And this works. It might not be what the caller expected because you said you'd give them a list of integers, and they had to give you a list of integers. They might not have expected that the returned list was the same as the input. It works though. It absolutely works, but in practice it causes problems.
Other stuff might not work after this.
Yes, yes, this function works, but not the other one. So there's a way to do this that's a little more functional, and it's specifically functional because it doesn't mutate state. It was brought up earlier that one of the key components of functional programming is that you're stateless and that you're not mutating some state outside of your world, which this first version here absolutely does. It mutates this numbers input. So what we can do instead is we can just new up another array list, and for each number in the numbers that are passed to us, we'll just add it onto our result list. And so this is nice for a lot of reasons, and I think most people who program in Java are already doing this. They're not, we learned quite a while ago that if you're going to mutate things, you're going to get bitten by it eventually. So if you don't control the thing, you should probably not be changing it. So there's another language that I like called Scala, and here's how you might do the same sort of thing in Scala. We might define what it means to increment a number, and we can do that by just saying inc is this thing that takes an integer, and then what you get out of it is that integer plus 1. And I can call that, I can say, inc1, and it'll give me 2. Now similarly, I can define incremented list as just taking a list, an iterable of integers, and then mapping this increment function over it. So this is the first time we've seen one of these iterable functions here. This one, map, does everyone here know what that does? I know a lot of you do, but is there anyone here who doesn't know what it does? Yep. Okay, so map is it's a collection operation, and what it does is essentially what the other it's an abstraction for what that other thing was doing, where it took the list that you gave it and it returned a new list of the same size, but where every value was transformed. So what map does is essentially that you give me a list of 1 to 10, and if I apply this function to it, I'll give you back a list of 2 through 11. So it's important that it's a 1-to-1 mapping, that it's the same length, the same shape, but we just take every value in the list and we apply this function to it. So this is our first example of a high order function. So when I program Scala, I like it hot. I like it higher order, and I like it typed because so. Oh, okay, I'm gonna go cry. No, so there was this phrase in the buzzwords category earlier called higher order function, and all a higher order function is a function that either takes in functions as its parameters or returns them as its result.
Yo, dog, I heard you like functions.
So I took a function, I gave you a function. So this ink is a function, and because map takes that as a parameter, as one of its inputs, we can say it operates over functions. Because of that, we call it a higher order function. So that's how you can use, it's a trivial example of how you can use functional programming to get rid of this sort of very boilerplatey iteration management. So this idea of higher order functions is kind of all over. It's very pervasive. If you've used a programming language called JavaScript, it supports higher order functions. So I can take a number list like the numbers 1 through 6, and I can take a function which tells me whether a number is even or not. So I can do that just by saying, this doesn't really matter how it works, but the fact that this will return true or false depending on whether or not each a given input satisfies the property that we're talking about. And so we can say that this function is like a property. We could also say that it's a predicate. There's a lot of different words that we can give to this. But we can see that when we say filter out just the ones that match, and we say nums.filter even, we get just the even numbers. So this is really, really powerful. We don't have to think about how we iterate. If we can just have a function that we want to use, we can apply it to a larger context. And I really like that functional programmers do it at a higher order. Ooh. Ooh, yeah.
That's hot.
So the other.
This might be my last meetup.
I'm sorry.
You're lost, buddy.
Yeah. The other part of the collection-oriented functional, trifecta is reduce. And reduce goes by a lot of names depending on what programming language you use. You might see it called fold, you might see it called collect or inject. But what's going on is you're taking many values and you're reducing them or boiling them down into a single value. So if I've got like a list of 0 through 9, like up to 10, and I want to reduce that using the plus operator, it'll give me 45. And the reason that happens is we can see it here using the reductions function, which just gives you each state of the transformation. So we can see that first we start with 0, and then we add 1 to that, and that gives us 1. And then we add 2 to that, and that gives us 3. And then we add 3 to that, and that gives us 6. So we can see that we're applying the next element in the list to the former accumulated value. So reduce is just a way to kind of fold these things together. It's very I think it's one of the most powerful parts of collection-oriented functional programming. And so some takeaway about working with collections. So reduce is this thing that can take something you can iterate over, which isn't just a list, it's just something that can yield new values to you. It'll take that thing and it'll transform it into a result. And what's really interesting, if maybe non-intuitive, is that map and filter are just special cases of reduce. That if you think about that definition before, that it transforms something you can iterate over into a new value, well, map fits that definition because it takes a list and returns one of the same size. Filter meets that criteria because it takes a list and returns it of the same or less. And the other key insight is that every time you're doing an iteration, every time you say for, you're doing one of either two things. You're either reducing out a new value or you're doing a series of side effects. So what do I mean when I say side effect? A side effect is something that changes the scope outside of the function. If it touches the outside of world, it's side effects. If I write something to a database and that thing can live longer than my program, than my little function, we can call that thing a side effect. Because it's not core to the thing that happened, it's something that happens out on the side.
Would you say if it's visible to anything outside the function?
Sure, sure. But I really want you guys to think about this and see if you can disprove this. See if you can think of a sort of iteration that is not either creating a new value or changing the outside world. And if you can, let me know. So I said that I
challenge you.
I said that map and filter are special cases of reduce. And I also kind of showed what reduce does, but maybe it's a little easier to actually see how it's implemented. So reduce, we take a reducing function, some iterable, and some initial value, and we say, well, the first result is going to be that initial value you gave us. And then for each of the iterable, I'm just going to make the result be applying the function given that result in the x. And then finally, we'll return that result. So you can see why plus works here on a list of numbers, because we say, we have 0 and then 1, and then we have 1 and then 2, and then 3 and then 6, or 3 and then 3, which results in 6 and then 4. So how do we define map in terms of reduce? Well, all we're doing is we build up a new list. We start for each element that we walk over. We just make a new list by adding to the end of it the application of that function over the element. So we can just say, and we'll be sure that reduce will worry about this iteration for us. All we need to worry about is building the list and applying the function. Filter's the same sort of way, except you use the function as a predicate. You say, either if this function is true, then I'm going to do the same thing that map does. I'm going to just append you to the end. And if it's not true, I will just do nothing. I'll just skip that one. And effectively, by skipping that one, you drop it. So this is, I think, the first sort of where you can kind of start to see that these things build off each other.
Okay.
That's right. The call is coming from inside the code. And I think that's one of the key power of functional programming, is that you start to define these things that are functions, but they become building blocks. They become units of abstraction that, like in that image in the beginning, you can sort of stack them on top of one another. And on the stack is actually where it happens, but it's a different talk. So we've got some functions. One of them makes a person. If you give it a name and an age, I'll give you back an object representing that. Very, very simple object. So I've got a brother named Eric. I've got a list of people, me and my brother. And what I want to do is I want to get the names. I just want to know what our names are. I don't really care about our ages for this particular thing. I just want to get our names. So a way I can do that is I can just map this thing that selects the name over this list. And that's it's pretty powerful, but what if I wanted to get the age out as well? The simplest way would just be copy pasta. You could just take this thing, Control-C, Control-V, change name for age. But that gets a little hard to maintain, because if you ever want to change something about that, you have to change it everywhere.
Easy versus simple.
Right. So what we can do here is we can just use one of these functions to set up that extraction of an attribute as this thing called get. And we can say, if you can tell me get an attribute, I can give you back a function that will select that attribute out of an object that I get. So this is a higher order function too. It doesn't take in a function, but its return value is a function. So it, just like map, is another example of a higher order function. So this get name brothers is exactly the same as this block up here. And it's less code, which I think is a real benefit, because you test get once and you know that every usage of it works. You test map once, and you know every time you use it, it's going to work. You don't need to go and test all of these little.
You test map once.
You don't.
I've tested at least
If
once.
you write
It's an
map,
empty map.
if you write map, you test it once. If someone else writes it, you don't test it at all. That's my rule, at least. So there's this thing called pluck, and say I want to say I have a list and I want to just select all the ages, because I see this sort of repetition here. It's like I've got age and I've got name, and even this is the same pattern that repeats over and over and over. And so we can also extract that at a higher level, because what's going on is it's just taking in an attribute in a collection, and it's just calling getAttribute and then mapping that over the collection. So now we can just say pluck the age out of the list of brothers, and now we've got a list of just the ages. So I think this is incredibly powerful. These are built, these are built on a tower of abstraction. So map, remember, calls back into reduce, which is doing these weird things with this pointers, but we don't need to care about that. What we care about is that we've got these things we've defined by functions, and that we're composing them together. And I think the composition of single responsibility functions is really so powerful and so beautiful. So another example, what if we wanted to invert filter? Filter is really cool, but what if I wanted to reject them? What if I didn't have a function called odd, but I had a function called even, and I just wanted to reject the evens? Well, that's the same as saying filter odd. So could we write something that can take even and pretend that it was odd? Well, it turns out that even and odd are these things called complementary functions, which really just means if one returns true, the other returns false. So we can define those. We can define complement. And this is another higher order function. It both takes in a function and returns a function, but all it does is just negates the result. So all reject is just filtering over the complement. So here's another example of just the way we can build these little blocks and compose them together. So like if you only take one thing away from this talk, it's that you should think about functions as units of abstractions. That you can give a name to an operation, and you can make sure it just does only that operation, and then you can build all these things together.
I can't stop watching.
Really mind blown.
I try to look away, and now I'm looking at your screen. I literally can't look away.
That's right.
Mindstorms.
So let's talk about functional problem solving. How can we use this style of using functions as building blocks to actually solve problems? It was kind of neat that we can build, I can write this thing called reject, but honestly I could have written that without functional programming. Every example I've given here I could have done without functional programming, and I would have been really just as good if I hadn't done that before. But I think the key insight into functional programming is that you take a problem and you turn it into a smaller problem. And then you solve that smaller problem in terms of a pure function. And then you repeat that over and over and over. So you can look at this MC Escher drawing, and it doesn't really make a whole lot of sense. If you look at any one part, it might make a little bit more sense. Like if you look at just one quadrant, it's fine. But when you try to look at the whole thing, it becomes a little disorienting. And I think solving problems with computers is a lot the same way. So what you can do is, like I said, just break it into smaller problems, use functions to solve those problems, and then repeat. So one of the patterns we use to do this is called recursion. If you don't understand recursion,
now you do.
Look at this GIF. GIF, I'm sorry. Yeah, you're right. No, this one isn't too useful.
It doesn't return.
In a problem solving, yeah, because it's an infinite loop. So the first thing you want to do if you want to use recursion to solve problems is you define a terminal case. You say, when am I done? Now, an example of that is like, I've seen this teapot 100 times. I'm done already. So like,
Tail recursive.
is it? Yes. Yes. The last thing is the call to itself. So if you can define your terminal case, if it's I've had enough tea, or I've seen this pot 10 times, so I'm done already, then you're one step closer to having a solution. Now the other thing you need to do is define what's called an inductive case. And all an inductive case is some condition that gets you a little bit closer to that terminal case. If you can do those two things, you can write recursive solutions. So these are kind of weird conditions, maybe a little mathematical sounding. So let's see examples. So an example is I want to define factorial. Factorial is just I've got like factorial 3 is 1 times 2 times 3. And factorial n is 1 times blank to n. So what we say is, if it's 1, that's the terminal case. 1, like if you ask me for factorial of 1, I know the answer already. It's 1. Any other number, I don't know. But I know that I can define a case that gets me a little bit closer to 1. And the way I can do that is you give me a number, I'm going to subtract 1 from it. And then I'll apply it, I'll multiply my accumulated value by that factor. So just by having a terminal case and an inductive case, remember when we end and how we get closer to that end point, we can define a recursive solution. Here's something that kind of looks right, but is very, very wrong. So I have a terminal condition, that's true. If the number is 0, then I'm going to say yay. But if the number is greater than 0, I'm going to increment it. And if it's less than 0, I'm going to decrement it. So both of these cases actually take me farther away from the terminal case.
Oops. Feedback.
Right.
But
So
how long?
well, until the stack
As big
blows.
as your stack is.
Yeah.
Or until the GIF ends.
Right.
No, that's a terminal case.
Yeah, when the stack blows up.
You get closer to the end
Imagine
of the
that I
stack.
trampolined it. So even though it looks like it's an inductive case, it really has to move you closer to that terminal case for it to really be what you need. So another example of this is like the Fibonacci sequence. I want a program that gives me the nth Fibonacci number. So if it's less than 2, like if it's 1 or 0, I'm just going to return that thing. Otherwise, I know that the way to get a Fibonacci number is by adding the 2 numbers prior. So just literally here I can say, just give me the 1 before and the 1, 2 before. And that'll be my solution. And because these will both get a little bit closer to this terminal case, eventually, hopefully, it'll say 1 or 0. I can define my problem in terms of these. This is actually incredibly slow, and I don't recommend you write programs like this. But it does definitely represent it's a good case study. So is everyone kind of still? Does everyone follow this? Does everyone? Yeah.
So the functional paradigm is not good for all cases, right?
Absolutely. Well, so we can.
Absolutely yes or absolutely no?
Absolutely yes.
Absolutely.
There is no case where functional paradigm is not good.
Yeah.
I can assure you that.
So yes, this is not functional programming's fault.
This is not functional programming's fault. Yeah?
Right. The problem here is that I'm doing more calculations than I need to. So.
Yeah, it's not ideal, is what I mean. You could do it, but it will end up in returning you a solution one day.
Functional programming always gives you better results than other functional programming.
There's this quote by Alan Perlis. It's functional programmers know the value of everything and the cost of nothing. So I can tell you what the value is, how long it's going to take. I don't know. So let's talk about where functional programming is actually used in the real world. So I think one of the coolest solution, and why you might have heard of it already, besides the fact that you guys already use it and love it, is parallel processing. If you define things only in terms of inputs and outputs, there's no thread safety to worry about. It's only ins and outs. And what you can do is you can use this pattern called divide and conquer, where you take one problem and then you break it apart into little subproblems, and then you use distributed computers to solve these problems, and then eventually you aggregate those results back in. So you just split it apart and then merge it back together. And that's actually what's going on in MapReduce. So what we do is we map the inputs and then we reduce them into some output. There's others. There's SAMZA. There's Storm. These are both kind of stream processing systems. And then there's also a tool called Spark, which I think is really, really awesome. It's kind of taken functional programming and something like MapReduce and kind of stacked them on top of each other. So let's give an example of what something like Spark does.
Can you please silence it?
I know, I'm sorry. So the classic distributed program is called word count. And what you want to do is you want to take all of the sentences in some huge, huge space, say every book in your local library, and you want to find out the frequency of the words that are used. So if any of you guys have looked at these examples before, the MapReduce framework, it's probably about 200 or 300 lines of code to get this sort of thing done. This is using Python. But what you do is you just load up some files, some distributed files on your Hadoop distributed file system. And what you do is you transform each line into a series of words just by splitting by the spaces. So if I say, hi, how are you? I'm just going to take every single space and I'm going to split it into a new collection. So now what I've got out of this is a list. FlatMap will take that list and turn it, and it'll basically concatenate every list together. So it maps the operation and then it flattens the results. When we have that, we can map each of these words into the frequency of 1. Because if I've got a word, I know that it appeared once. Then what we can do is we can reduce by the key. So we've got duplicate keys here because if I said the word hello more than once, I'm going to have this pair hello 1 there multiple times. And I say hello is the key. So then I take this 1 and I just add them all together. I use reduce to reduce the keys into one result set. So if hello was there 100 times and I add 1 100 times, now I've got the frequency. So this will actually go and give you out the word count. And if you look, the way it's doing it is by just taking these pure functions and composing them together in an interesting way. And again, this distributes over thousands of computers if it needs to. The other place you might see functional programming is in...
if you have them.
If you have those computers, yeah. It won't do that on other people's computers.
Not yet.
Yeah. So another place you might have seen it is there's been a big shift in the UI programming world towards functional programming. Some of those is like Facebook's library React. There's another one called Elm that one of the guys at Google made. Another is Ohm, which came out of some work at the New York Times. There's one called PureScript, which is like a language entirely unto itself. And there's another one called Bacon. And what these let you do is they let you control a user interface in the same sort of terms that we've been discussing.
Don't you think that jQuery should also be mentioned? Because jQuery is very heavy functional programming.
jQuery is very functional until you work with the DOM.
Until it's not.
What was that?
jQuery is like JavaScript.
Not quite. It is functional programming based up to very big extent.
Yeah. So AJ just mentioned a library called underscore, and they actually call themselves like the suspenders to the jQuery tie. It's like the functional toolkit to add on to jQuery, and it provides a lot of these things we've seen before. So let's look at an example of what this sort of stuff looks like. So if I want to use a library like React, and I wanted to use my functional principles that I've been learning, how would I do it? If so what this is going to do is it's going to define a component that's going to list a bunch of people. It's a people list component. You can tell that by this line right here. It says a people list. So what we have is we've got some properties about ourselves. We've got our friends, which are, just the people that we like, and we've got the followers, which are the people that like us. Now, people are both of those things. So what we can do is we can concat those two lists together, and then we can filter by just the ones that are my favorites. And then of those, we can sort them by those who have the most followers, and then slice to take just 10 of them, and then map them into a DOM element, into a div in this case. But you can see that we've just got these pure functions that only operate in terms of their inputs, and they return just outputs, but we're able to actually build UIs using this style. And I think it's really, really powerful and really, really clear and simple to think about. So I'm kind of reaching the end, but this is really just the tip of the iceberg as far as functional programming goes. Some of the things that I think are very, very powerful that I didn't get time to talk about, that I encourage you guys to go look up if you're not familiar, are lazy sequences. And what these let you do is they let you represent possibly infinite sequences, but the important part is that the creation of these things is actually delayed, it's deferred until they're needed. So rather than building up this huge report up front, you wait until someone asks for it and then you deliver it.
But that's not quite functional programming technique, that's general optimization technique.
Yes, but if you want to transform lazy sequences, you do well to use functions. Another is generics, and this gets into this kind of ties into thinking with types. If you want to define something like map, and you want to do it in a type-safe way, you're going to need another one of those buzzwords. So in the beginning, you're going to need parametric types, also known as type generics. They're the same thing. And what it is it means the type that this function operates over is a parameter like any other. So I can operate over a list of something. I don't know whether it's a list of integers. I don't know whether it's a list of apples, a list of oranges. That's an example of the parameter. And so if I am parameterized by type, we can say that I am generic over types. And I think that thinking in terms of these types and using types not as sort of like a crutch or a restriction, they can actually be a tool, and they can help you know what sort of operations you can do. So the rest is just questions. If you guys want to talk, if you want to have a discussion. I want to know, has functional programming gone too far? One weird trick to make object-oriented programmers hate you. No, that's it. That's the talk.
Just want to mention Thomas Omens works with us here at CJ.
And no one else?
That's right.
We have a lot of spots open, so if you want to work with a brilliant guy like this, it's really fun to be with.
It's true, we're hiring.
Talked to one of our recruiters,
Yep.
like Eric over there, who told me to do this. That's why I'm doing it. I don't like shameless plugger.
It's so hard to sell.
If you guys want to write code like this, I mean, it's a thing we do.
Wait. But working with Thomas comes with disclaimers.
That's true.
You also have to work with me.
You almost have sold me up to this point.
Exactly.
Thanks, Melanie.
No, so you guys said the crowd here, it seems predominantly functional. So do you guys get to use functional styles in your day-to-day work, or?
Absolutely
Yep.
everything.
And
Everything functional.
would you go back? Would you? Do you say you mix and match often, or do you say it's does it like dominate your programming style? Is it?
It dominates.
Yeah.
It dominates.
When isn't it practical? When is it impractical?
When is functional programming not practical?
If I write hello world program,
Well, it's definitely built up on a lot of. I think if you're going to write functional programs, you need to be in an environment that supports it. Because I think a lot of the things,
Like programming microcontrollers, probably not so much.
right?
I wouldn't say even I mean microcontrollers.
Well,
are
actually, you know, you're never full of engineers. Well, I know how to do that.
It'd be like VHDL, trying to define ASICs.
Yeah, VHDL is functional programming in essence. So, I mean, microcontrollers were traditionally and FPGAs were traditionally done in functional programming. So, no, it's all functional programming, baby.
Yeah.
What languages do you use for your functional programming?
Well, I predominantly use Delphi, but yeah, I mean C++ as well. And, so yes, the new C++ 11 it has functional programming capabilities.
I mean, it's functional programming can be in any language. It's a discipline.
Yes.
It's one of the hardest things I do is to instill that functional way of thinking to my Java programs. I mean, there are very few cases where you need mutable state, even in something like Java. It's when you get to the pragmatic parts, when you get to the parts where you've got to make your code marry some environment. That's where you end up with mutable things. But if you can force all your mutable stuff into those boundaries, you can program everything else functionally. Yeah. Well, actually, because inherently our architectures are not. I mean, non-human architectures aren't functional. They have a instruction pointer and they say do this, do this, do this. So at some point you have to convert between your functional expression and your code and the stuff that actually does stuff on the processor. So wherever you're meeting the sort of pragmatics is where you need to do your mutable stuff. But I try to instill in everybody that pushing that down and delaying that stuff as long as possible will give you the most testable, the most maintainable and easily understandable code.
Yeah, I think programs with side effects are the hardest to reason about, and so I think it's not that you can program without side effects. I think that.
But you can reduce
show something on the screen. That's a side effect.
But what you can do.
The first thing you did with that Python function, how would you write a test for that?
It works once.
So, does it have an advantage of better performance than object-oriented programming?
In general, yes. It is faster.
I think the point is that
it is shorter code,
Yeah.
more maintainable code, because I mean, see, in traditional programming, including object-oriented programming, sequential-based, okay, I tend to call it sequential-based programming. In sequential-based programming, you always focus on, okay, I have to do this, then I have to do this, then I have to do this, then I have to do this, in certain order. So you describe what needs to be done. In functional programming, I mean, if you do it right, you just say, no, I want this to be achieved. I want this to be achieved. And I really don't focus on how it gets achieved, but actually what needs to be done.
So I think if you talk about performance of functional programming, I think if you use functional programming as a way to eliminate clock cycles, you're probably going to fall short. But if you use it as like developer performance or being able to deliver software, and software that is fast, I'm not saying functional programming is slow, but absolutely, like procedural, like twiddling bits at the assembly level is going to be faster.
And also
because of abstraction.
Very questionable because, I mean, you're coming to the argument which goes all the way to assembly language programming, right? Theoretically, the fastest way to program something fast, I mean, not the fastest way to program something,
slowest way
but
to
to make,
program.
yeah, the slowest way to program something to execute the fastest is supposedly assembly language. But in assembly language, you do local optimizations. And local optimizations, they don't pay off.
Well, they pay off locally.
Well, they pay off locally, but your application executes actually slower. So if instead of that, you focus on the overall architecture and how everything to be architected into a highly optimized architecture, you actually get a much better benefits, including with things like lazy evaluation, which you mentioned, and stuff like that. So you can get optimizations which gives you orders of magnitude increased speed versus increase the speed of, let's say, 10-15% to some local optimization. It doesn't the difference.
And also because of referential integrity, you get to scale in ways that you never could imagine. I mean, you can just throw hardware at it. I mean, if nothing has a side effect, then I can throw
parallel processing is
like developers.
Right, exactly.
Is there a cost to the abstraction? Not dealing with the nuts and bolts. When you start abstracting things out, it implies a
yes, depends how you do it.
The most expensive
if you know what you're doing.
Yes,
you've got to get the right to start with, or you get real
I'd say actually no in a functional case because it's you're building on abstractions by composition, not by extension or inheritance.
Well, it's the same argument. It's the same argument I have heard before. Whether or not C++ gives you a faster and better optimized code than, let's say, C code, right? So in C code, you don't have virtual functions and you don't have all of those things. Well, what happens is instead of virtual functions, you have to use a lot of if statements and all kinds of things, which can be handled with virtual functions. So which one executes faster, a virtual function which gets the reference to assembly level to a vtable, or an if statement? Well, the vtable actually is going to execute faster.
The abstraction I'm thinking of is more like the business logic for your system and how your company thinks about it. When someone comes in from the outside and they're looking through this code base, if they don't know how you think, it's going to be very difficult to traverse through, debug, to extend and that kind of stuff.
So functional programming by itself isn't going to help you write clean code. No, there's no substitute for clear thinking.
I disagree. The more I learned about functional programming, the more I became embarrassed about the imperative stuff I've been writing.
Yeah,
and how
I
really
there's a false distinction here that a lot of people get in their minds. It's types on one side and functions on the other, and I was really thankful that Thomas kind of pulled that out here in the talk, that types and functions actually can go hand in hand, right? So you can, coming from the object world, you don't have to throw away types if you like that, right? And I like types. In fact, you can use the good parts of what you use types for to, in a functional way, build up abstractions, right? And collect functions and organize functions in the right way, which throw away is the mutable state. And that's really not relevant to your model, right? If you had mutable state, it was really never kind of orthogonal to your business model, right? And in fact, in a lot of ways, it probably confused your business model because it was wrapped up in the state machine.
Yeah, I mean, you can think of functional programming. It's not enemy of object-oriented programming. It's actually a complement. Because the object-oriented programming was describing the objects, right? And you were supposed to describe some kind of capabilities of those objects through member functions and stuff like that. The functional programming actually complements that and is similar type of step because it basically describes the relationships of anything, right? So you're describing anything in the form of model. On one side, you still can use object-oriented programming to describe the model of the objects you're modeling. And on another hand, you use the functional programming to describe all of the relationships in the form of relationship rather than I do first this, then I do this, then I do this. So this is this type of modeling. And the two actually complement each other quite well.
Object model is great.
Yeah.
Object decomposition is not at all anti-functional.
Exactly.
You need both to model a problem well.
Exactly.
You need to say, these are the types. I'm going to expect collections of these things, and I'm going to expect, lookups of these things and all that. But when I get time to express the computations are expressed in a way that is more declarative in a way that I think is much more readable. Especially, you said when people are coming in and trying to read it, it is a big change. I mean, it is. I mean,
but I've also seen object-oriented programming that you come in and you try to read it.
But everybody's been trained in school, to do
step by step
in imperative programming. Functional, I don't think is really. Maybe it is now.
So I would say that is exemplary of the simple versus easy thing I was trying to talk about. That just because you can see it, and it is very complicated because there are these mutations, because it's familiar and easy, you might come in and say, oh, I can understand this. Whereas simplicity, no matter what paradigm you're using, if you've got to focus on single responsibility and simplicity, it's going to be, there's nothing like it.
If you're in a language you're familiar with, you're going to be able to understand it. If you're used to Java and you start looking at Clojure code and you never heard of Clojure or Lisp, and you're like, what is going on? What's all these parentheses? It's going to be complicated. You're not going to understand it until you understand the language you're dealing with, regardless of the paradigm that you're talking.
You have to internalize the syntax so you can recognize things in bigger chunks than one word. It's like when you learn to read, you learn to see. Eventually, you learn to recognize paragraphs, and you can almost read a sentence without even thinking of that sentence.
So, what's the advantage of using the functional paradigm that sort of takes the imperative brain and turns it inside out? When you get out of colleges, people who know imperative programming style
go somewhere else.
Well,
you just turn them away. Well, here's the one thing: you can entirely categorically eliminate an entire class of bugs.
Yes.
Absolutely.
And you're not going to eliminate all bugs, and you can still write portable code, but nobody can stop you from that. Right?
And it has to go hand in hand with things. Like one of the things that I really instill in people is that you have to name things correctly. You have to. Just because you're a functional.
That's my point about abstraction, and I come from a biology background where you build models, but when you get down to the details, one person says, I'm looking at it from this way, and I see this, and it looks like that, and it does that. The other person sees it at another point in time, same thing, process, whatever, and it's totally different research paper.
That's all about
software is way easier than biology.
I had a problem today where a programmer had written some code that caused a major bug in one of our software pieces of release. And it all came down to a naming problem. He named the functions, or he named a property has audio channel or something like that. I forget the exact thing. But that didn't express that it was only actually applicable to video presentations. And so other people have written is that any presentation could be checked, or if it had an audio component, didn't apply to actual full-on audio components, and we actually lost days of effort trying just because somebody named something wrong and another person misunderstood their name. So it's still about, you still teach good design and good naming and things like that.
Fundamentals, yeah.
Okay. Cool. No one started a question for half a second. We're done.
Well, we should move on to our light and talk section. We've got 2 people signed up so far. Was anybody inspired for the light and talk?
I think I might start using functional programming after that software.
Yeah.
What is in your GM?
Yeah, we're always just.
Can I start 5 minutes after bio? Yeah, 5-minute break. How about 5-minute bio break?
Where are the bio